So now we can look at entropy and enthalpy and determine if a reaction is spontaneous or not. So we're going to apply these concepts to the idea of something reacting spontaneously. Remember that heat at constant pressure equals enthalpy change. Delta H is the same as Q at constant pressure. Since we said the second law, delta S is always increasing for a system, and that it's greater than the heat at constant pressure over T, and we saw this earlier. So that's the same as delta S is greater than delta H over. We can rearrange this equation and bring the delta H over and multiply by T, and we get this equation. Delta H minus T delta S is less than 0 for a spontaneous reaction at constant temperature and pressure. So this means that that quantity, delta H minus T delta S, has to be a negative number in order for a reaction to be spontaneous. If delta H minus T delta S is positive, then the reverse reaction is spontaneous. The reaction in question is not spontaneous, but the reverse is spontaneous. And if delta H minus T delta S equals 0, the reaction is considered to be at equilibrium. All right, so this quantity now has the American physicist Willard Gibbs decided to call this quantity free energy, or Gibbs free energy, and it's given the symbol G. And so G is defined as H minus TS, or since we really like to talk in deltas, delta G equals delta H minus T delta S. And this gives us a direct way to decide if something is spontaneous. Okay, so delta G equals delta H minus T delta S. This is the definition of Gibbs free energy. If we can show that delta G is negative, then we can predict the reaction will be spontaneous. The standard free energy change, delta G with the little circle, means standard. And again, that's when reactants and products are in their standard state, which means 25 degrees, 1 atmosphere pressure. If it's a liquid, if it's a solution, it's 1 molar solution. And so delta G standard delta G equals delta H standard minus T delta S, which is all we're going to work through really is standard pressure, temperature, etc., concentration. All right, so what is the standard free energy change for the following reaction at 25 degrees Celsius? Well, we already know how to find delta H, and we already know how to find delta S from the tables in your book, and so we can do this problem. So what I like to do is put the number below each symbol just to make it a little bit easier. So my delta H values, remember, for pure elements are 0. For gaseous, again, be really careful when you're looking to make sure that you have the right phase, because some compounds can be in more than one phase. So NH3 gas is negative 45.9, so we have to multiply that by 2. And then we can also look up the S values for N2, H2, and NH3. Make sure and multiply them by their coefficients. Now we can calculate delta H and delta S. Delta H is just the products, the sum of the products times their coefficients minus the sum of the reactants times their coefficients. So NH3 is negative 45.9. We multiply that times 2, and then of course the reactants are 0. So our delta H is negative 91.8 kilojoules, which means this is an exothermic reaction. Delta S is the same way. You take the products times their coefficients, sum those together, minus the reactants times their coefficients. Be really careful when you do the math. I would definitely add all the reactants together all the products together first, which in this case is just NH3, so 192.7 times 2, and then add together all the reactants before you subtract. Otherwise, you'll have to distribute that negative sign all the way across. So be really careful with your calculations. So N2 is 191.6, H2 is 130.6, and we have to multiply that times 3. So if we add all that together and then 2 times 192.7 minus that quantity will give us negative 198.0 joules per Kelvin. And this hopefully makes a little bit of sense to you, because if we look at the reaction, we have 4 gas molecules on the left, we only have 2 on the right, so we're becoming more ordered, so a negative delta H should make sense. All right, now we can substitute it into our equation for delta G. So the one really important thing to remember is that if you haven't been paying attention, delta S is always in terms of joules per Kelvin, and delta H is always in terms of kilojoules. And so we have to convert one or the other before we add them together. So usually we convert S from joules to kilojoules. So delta G minus delta G equals delta H minus T delta S. So delta H is negative 91.8 kilojoules. T is 298 Kelvin. You always want to make sure that it's in Kelvin. And then delta S is 0.198 kilojoules per Kelvin, negative. And so notice that the Kelvin will cancel and we'll have kilojoules minus kilojoules. And actually because it's a negative delta S, that whole second term becomes positive. And so we have negative 91.8 plus 0.198 times 298 is 59. And so the total is negative 32.8 kilojoules. So is this reaction spontaneous or not spontaneous? Well, because it's negative, it's a spontaneous reaction at 25 degrees Celsius. So it actually turns out that they have tabulated the standard free energy of formation for delta G Fs for all the substances, or for many substances. And just like delta H and S, the standard free energy is going to be at 1 atmosphere pressure at 25 degrees Celsius, and if it's a substance, if it's dissolved, it's 1 molar. And so just like delta H sub F, these are the delta G's, the free energy change that occurs when 1 mole of substance is formed from its elements at standard temperature and pressure. And so we can do the same thing that we've done with delta H and delta S. We can tabulate, we can look up the delta G values and sum them up. So we take the products times their coefficients minus the reactants times their coefficients. And you can look up the values either in table 18.2 or at the back of your book. So we can do an example here, and actually if you step back and look at the previous example of ammonia where we used delta H and delta S and plugged it into that equation, you could also do it by looking up the delta G values and you would get the same answer. You might actually be slightly off depending on rounding errors and things like that, but you should get really close whether you use delta H minus T delta S or whether you use delta G, a formation from the chart. You should get similar results. So use the standard free energies of formation to determine the delta G for this reaction. So again, we need to look up the values. And so the delta G of formation, and just like the delta H's, if you have something in its elemental form, of course, to make it from its elemental form is 0. So it's only S that's not non-zero. So, and don't forget to multiply it by the coefficients. And so we have products minus reactants. So in this case, we use the summation law, and we have 2 times negative 394.4 plus 3 times negative 228.6. Take that quantity and subtract 1 times negative 174.9. get a delta G of 1,299.7 kilojoules, and it's positive. So does this reaction happen at 25 degrees naturally? This is a non-spontaneous reaction. So strictly speaking, if delta G is less than 0, that reaction is considered spontaneous. But we usually have a little buffer zone. So generally we say if delta G is less than -10 kilojoules, then we consider that reaction spontaneous as written. In general, the reactants will transform almost entirely to products when equilibrium is reached. And then, strictly speaking, if delta G is greater than 0, it's non-spontaneous, but generally we say if it's greater than +10, it's considered non-spontaneous as written. So reactants do not give significant amounts of product. However, the reverse reaction would be spontaneous because you're going to get the same value but opposite sign if it's the reverse reaction. And so then, of course, if it's between -10 and +10, we consider that reaction to be at equilibrium with a mixture of significant amounts of both reactants and products present. So spontaneous reactions theoretically can be used to obtain useful work. So for example, we use a combustion engine, gasoline, to move an automobile. And so the spontaneous reaction, we collect the energy that's given off during that reaction, and we're able to do work. Often, however, reactions are not carried out in a way that does useful work. So for example, if we just put the reactants together in a reaction vessel, no work is done, like when we did the zinc and hydrochloric acid, but we didn't put a top on it. We didn't collect that PV work. And another example is spontaneous precipitation reaction occurs. The free energy of the system decreases, entropy is produced, but no useful work is obtained. So you have to be careful to get the work out of the system. So, but why is it called free energy? Well, it turns out that if a reaction is carried out to obtain the maximum amount of useful work, then no entropy is produced, and so W max is equal to delta G. And so it basically means the term free energy says it's the maximum amount of energy available or free to do useful work. So it's usually not all used to do useful work, but that is what it's available to do that work if it can be used. So again, in real situations, it's not possible to reach this maximum work, and some entropy is created, and that's why entropy is increasing. But delta G gets its name, free energy, because it is the amount of energy free to do useful work. So as a system approaches equilibrium, the instantaneous change in free energy approaches 0. In other words, delta G approaches 0 when it's near equilibrium. We can illustrate that on the following figure. So generally what happens as a reaction proceeds, the free energy decreases because it's being used up, and eventually it reaches its minimum value of basically 0. So delta G equals 0, the reaction is at equilibrium, and the reaction stops and we are at equilibrium. So this is what they're talking about. So we start out with some free energy. As the reaction takes place, that free energy decreases, and eventually we come to equilibrium, which is when delta G is 0. What if you have a non-spontaneous reaction? You're going to go in the opposite direction. So non-spontaneous, if you're going from left to right, we have to go down a little bit to get to equilibrium, and then we would have to increase delta G to get up to products. This would be a non-spontaneous reaction, so it wouldn't go without something else making it go. So it's non-spontaneous on its own. So we can actually show how delta G is related to equilibrium concentrations. if you so delta G standard state with the little circle, we can show that delta G in non-standard states is related to the standard free energy change plus R, which is the gas law constant, times T, which is the absolute temperature, times the natural log of Q, which is, remember, the Q was the same as the K equilibrium expression, only we didn't know for sure if it was at equilibrium or not. So it was initial products divided by reactants raised to their coefficients. Okay, so delta G represents an instantaneous change in free energy at some point in the reaction as it's approaching equilibrium. So we're not at equilibrium. At equilibrium, we know that delta G equals 0 because we're approaching, at equilibrium, delta G equals 0. And then we also know that Q becomes K at equilibrium. So if we plug that in, we get this equation. All right, and so now we can rearrange it. And we get delta G standard equals minus RT natural log of K. So we can see how the delta G is directly related to the equilibrium expression. And just a note on the bottom, since we're dealing with units of energy, we use the value for R to be 8.31 joules per mole Kelvin rather than the liter atmosphere per mole Kelvin. So use 8.31 joules per mole Kelvin. All right, so let's think through this. If K is greater than 1, that means the natural log of K is a positive number. So the negative RT of times a positive number will give you a negative delta G. And so what does that mean? That means delta G, the reaction is spontaneous. So if K is greater than 1, which means products predominate over reactant, so K means, the numerator is bigger than the denominator, that tells you that it's a spontaneous reaction. So it makes sense that they go together. If K is less than 1, that means that reactants predominate because the denominator or reactants predominate. The natural log of a number less than 1 is negative. So a negative times a negative gives us a positive. So delta G will be positive. All right, so if you know the delta G for a reaction, you can plug it in and find the equilibrium constant for any reaction. So for example, find the K value at 25 degrees Celsius for the following reaction. The delta G for the reaction is negative 13.6 kilojoules. So actually in this case they're telling you what delta G is, but if you could also look in table 18.2 for delta G's or the back of the book, Appendix C for the values, and you can also find delta G by taking products minus reactants. I think you would have a hard time finding urea, NH2, CO, NH2, and so I think that's why this is already calculated for you. But anyway, delta G equals negative 13.6. It's negative, so we expect K to be larger than 1, and let's see what happens. So we can rearrange the equation. Delta G equals negative RT times log of K. Since we're looking for K, we've got the natural log of K, and we divide both sides by negative RT. So if we substitute the numbers in, you want to be really, really careful. You either have to convert R to kilojoules by dividing by 1,000, so then you would have negative 0.00831 in the denominator, or you have to convert delta G to joules, which would be multiplying by 1,000. And the reason why you want to do that is because you want your units to cancel out. And then also notice that Kelvin will cancel out. And so actually the numerator should be joules per mole. So the moles will actually cancel out too. So the natural log of K is 5.49. It doesn't have any units. So now to find k, we take the inverse log of both sides, which means take e raised to the 5.49, and we find that the answer is 242, which indeed is greater than 1. So because delta G is negative, we expect k to be greater than 1, and so since this reaction is spontaneous, we expect products to predominate. Okay, so what we want to do is sort of interpret delta G in terms of delta H and delta S. So let me start by saying, if you think of a spontaneous reaction, something that happens naturally, we tend to think that something that's exothermic will happen naturally because, well, it's giving off heat. But that's not always true. So many times a spontaneous reaction is one that's exothermic, but not every single time. And in the same way, we can think of something that is becoming more disordered. Well, yeah, we tend to think of things that become more disordered as happening spontaneously. It happens without anything stopping it. But not in every single case. And so a lot of it, as we're going to see, will depend on the temperature. And so what we can do is look at delta H and delta S in different situations and predict what's going to happen to delta G. And so, in other words, will it be spontaneous or not? So remember that delta G equals delta H minus T delta S. And so what we're going to do is sort of interpret overall signs here, and we'll pull up the table. So in the first instance where we said delta H is negative, which is exothermic, and delta S is positive, which is becoming more disordered, we tend to think of both of those as happening spontaneously. And in fact, if you plug that in, so if you think about a positive delta S, then that makes that whole second term negative because it's minus T delta S. And if delta H is negative, that means that delta G will be negative no matter what delta S and delta H are. As long as delta S is positive and delta H is negative, delta G will be negative at all temperatures. So that kind of reaction would be spontaneous at all temperatures. An example of that would be like burning gasoline, because it's exothermic and the molecules are becoming, we're going with something complex and we're breaking it down into something smaller, so it's becoming more disordered. The opposite is also true. So if delta H is positive, meaning endothermic, and delta S is negative, meaning becoming more ordered, well, a negative times a negative is positive, so the whole second term is positive, the first term is positive, so that reaction will be non-spontaneous at all temperatures. So if something is endothermic, if you have to put heat into it and it's becoming more ordered, it's not going to happen by itself. It's going to be non-spontaneous. But now we can have a little bit of a difference. So what if we have delta H being negative? So an exothermic reaction, however, it's something that's becoming more ordered. Let's see. So if we look at the second term is positive and the first term is negative. So in some cases delta G might be negative, and in some cases it might be positive. Well, how can you tell? Well, it's all going to depend on the temperature there. So if the temperature is low, that means that second term, actually the first term dominates. So if temperatures are low, that positive part will be small and the negative part will be big, and so delta G will be negative, and so that reaction will be spontaneous at low temperatures. However, if it's a high enough temperature, at a certain temperature, that second term will dominate, and the whole thing will become positive, which would mean non-spontaneous. An example of this is freezing ice. So freezing ice is exothermic. If you take ice and you cool it, if you take water and you cool it to become ice, you're actually going to release heat. It's exothermic. However, it is becoming more ordered. And so we know that that's spontaneous at low enough temperatures, below 0 degrees Celsius. It is not spontaneous at higher degrees temperature. So this is one where it's going to flip. Now the opposite of that is also true. So if it's an endothermic reaction, positive delta H, and it's becoming less ordered, where delta S is positive, well then at higher temperatures that second term will dominate and make it more negative, so it'll be spontaneous at high temperatures and non-spontaneous at low temperatures. An example of a reaction where that would happen is those cold packs. We know if we crack a cold pack, what happens is you're dissolving a salt, which is dissociating, and so it's becoming more disordered. However, it's absorbing heat from outside of it, and it's becoming colder, and so that would be considered a spontaneous reaction where it's becoming is endothermic, but it is becoming more disordered. So from that last discussion, we know that delta G is not always going to be the same with changing temperature. We are going to assume, though, that delta H and delta S do not change with temperature. So exothermic or endothermic, it doesn't really matter what the temperature is. A reaction will still be exothermic at all temperatures, and it'll be ordered or disordered regardless of temperature. So we can actually find out when a reaction is spontaneous or non-spontaneous. We can check at any temperature using this same equation, delta H minus T delta S. So because delta H and delta S are really temperature independent, we can use the same values. Now we know that delta G with the little naught means at standard temperature and pressure, but we can also find delta G at other temperatures by using this equation. So let's do an example. Find delta G for the following reaction at 25 degrees Celsius and at 1000 degrees Celsius, and then relate this to spontaneity. This reaction is calcium carbonate becoming calcium oxide and carbon dioxide. Calcium carbonate is what you find in chalk, limestone, and calcium oxide is quicklime, and so this is the decomposition of calcium carbonate. So the first thing you want to do, again, you can find delta G at 25 degrees because the tables are standard 25 degrees Celsius, but we can probably go ahead and just find delta H and delta S for this reaction and then use it at different temperatures. All right, so delta H for calcium carbonate is negative 1206.9, calcium oxide is negative 635.1, and carbon dioxide negative 393.5. Again, be careful that you're picking gas and not solid or liquid. Use the correct phase. All right, and if we look up S values, calcium carbonate is 92.9, calcium oxide 38.2, and calcium carbon dioxide 213.7. So all of these have a 1 for a coefficient, so we just add up the products and subtract the reactants. So delta H, products minus reactants, since all the coefficients are 1, we have negative 635.1 plus negative 393.5, and then minus a negative 1206.9 gives us a delta H value of 178.3 kilojoules. So now if we do the same thing for delta S, we take products minus reactants, and all the coefficients are 1 in this case, so it's 38.2 plus 213.7 minus 92.9, and we end up with 159.0 joules per Kelvin. Don't forget that S is in joules and delta H is in kilojoules. Notice that delta S is positive, so this is becoming more disordered because it's a decomposition. However, delta H was also positive, which means this is an endothermic reaction. So now we can plug it into the delta G equation. So don't forget to convert delta S to kilojoules per Kelvin. So 159 joules per Kelvin is the same as 0.159 kilojoules per Kelvin. Make sure and convert temperature to Kelvin, 298 K, and we can plug it in. So there's our equation, delta G equals delta H minus T delta S, and this will be at a different temperature. So at 25 degrees or 298 Kelvin, it turns out that delta G is 130.9. And like I said earlier, you could actually have looked up the numbers for delta G for calcium oxides, carbon dioxide, and calcium carbonate and get probably pretty close to the same answer. But notice that delta G is positive, which means it is non-spontaneous at 298 degrees Kelvin or 25 degrees Celsius. Now let's plug it in at 1,000 degrees Celsius, which is 1273 Kelvin. This time, again, the same delta H and the same delta S. Don't forget, again, to keep it in kilojoules. This time, delta G is negative 24.1. So the reaction is spontaneous at 1,000 degrees Celsius. And that's just what we would have predicted if we had looked at that chart back a few slides, that if delta H is positive and delta S is positive, it should be non-spontaneous at lower temperatures, spontaneous at higher temperatures. So we can actually go one step further and we can actually find the temperature where this reaction changes from non-spontaneous to spontaneous. And that is because delta G equal to 0 is that trade-off point, right? So if we go from positive to negative, it has to go through 0. So if we find out where what temperature will make delta G 0, then we know where this temperature change will occur. And so if we rearrange the equation, delta H minus T delta S equals 0. So now we bring T delta S over to one side and then divide both sides by delta S. We find this equation, the temperature equals delta H over delta S when delta G equals 0 will give us the temperature at the changeover. So in this case, 178.3 kilojoules divided by 0.159 kilojoules per Kelvin will give us a temperature of 1,121 Kelvin, or in other words, 848 degrees Celsius. So this temperature, this reaction will remain unstable. It should not react non-spontaneous up to 848 degrees Celsius, in which case it would become spontaneous. So another way of thinking of it is calcium carbonate is thermally stable until it's heated to about 848, in which case it will decompose to calcium oxide and carbon dioxide. So what should you be able to do in this chapter? You should be able to predict the sign of an entropy change by looking at the number of molecules or gas molecules, or if it looks like it's becoming more ordered or less ordered. You should be able to calculate delta S for a reaction or a phase transition by looking up the values either in table 18.1 or the back of the book. You should be able to calculate delta G from delta H and delta S. You should be able to calculate delta G from standard free energies of formation, which would be table 18.2, or again, appendix C. The third column is delta G. You should be able to interpret the sign of delta G as spontaneous or non-spontaneous, and also know how it relates to the signs of delta H and delta S. So so you should also know what the signs of delta S and delta H mean, and then how they all accumulate to make delta G, as that table that we talked about a few slides ago. You should be able to write the expression for a thermodynamic equilibrium constant. Be able to calculate K if you know the standard free energy, delta G, so be able to calculate K from delta G. And then be able to calculate delta G and K at various temperatures. So, using delta H minus T delta S at various temperatures, and then once you find delta G, you can plug it in and find K at whatever